University. She was then awarded a Hubble Fellowship in 2011, where she went to the Columbia University in New York, and she worked with Katherine Johnston on Catherine.
Yeah, Catherine married everybody.
Everybody there, okay, yeah. So she worked on simulations and local group stuff there. Shortly thereafter, she got a faculty position at the University of Arizona, and I think moved there in 14. Okay, so where she's been working on related issues. So she works on not only, like I said, Magellanic Cloud, first passage scenario, interactions between Magellanic clouds, the two Magellanic clouds, the Magellanic streams. She's also done a little bit of work on trying to understand the macho events, which were detected by the macho survey in the Galaxy, and try to understand what's going on with those things, which nobody still really understands. So, all right, so today she's going to talk about what she's been working on the past few years and right now, dynamics of the local group, challenging conventions in the era of precision astrometry.
Thanks, Louis. So, over the past 10 years, there's been new measurements of the three-dimensional motions of all the different members of our local group. And all of these measurements have completely changed our picture and perception of what's been going on in our local group. What's the history of our Milky Way and how has it interacted with other galaxies? And this may seem like a bit of a surprising statement. Your textbooks will lead you to believe that we understand our Milky Way and our local group quite well. After all, we've seen these galaxies since there have been humans on the planet. And, but what's actually been really surprising to many, perhaps, is that we haven't actually known the exact three-dimensional motion of any of the members of our local group, meaning our Milky Way, nearby galaxy M31, and the small galaxies that orbit around both of these galaxies, until fairly recently. This is really something that has changed over the past 10 years. And with every single proper motion measurement, basically the old picture gets thrown out the window. So what I'm going to do today is kind of give you an overview of some of the things that I think are the most surprising that have happened over the past little while, and what I think the consequences of those discoveries actually are. And I'll be highlighting particularly work that's come out from my students, Ekta Patel and Nico Garavito-Kamara over at the University of Arizona, and also in collaboration with a number of other folks who've been working with us to combine both theoretical predictions from cosmological simulations and just the amazing precision of the data that's been coming out for understanding the three-dimensional motions of galaxies using the Hubble Space Telescope and in the near future, James Webb. So, oops. There we go. Sweet. So here's our local group of galaxies. So here over here we have the Milky Way, and this is the Andromeda Galaxy. So these are the two biggest members of our local group. They're about 770 kiloparsecs apart. And then there's a swath of small satellite galaxies that orbit around the Milky Way and around Andromeda. So as of about 2015, we've known about 30 existed around the Milky Way and about 32 about Andromeda. So the ones I'm going to focus on in particular, the biggest ones, so our Milky Way and Andromeda, and then around our Milky Way are the two Magellanic clouds, large and small Magellanic clouds, and then around M31 there is M33, right? And M33 and the LMC are kind of similar in mass. So as of around, I think, starting in 2015, this picture of how many satellites are there associated with our Milky Way kind of just went crazy. All of a sudden people are finding new satellites around our galaxy, and this is because there's a new area of the sky that opened up, namely the south. So in the north here, so the Milky Way would be across this plane here, which is why there's very little data here, because we're just swamped with Milky Way stars. The northern hemisphere was covered by Sloan, and so all these blue squares are indicating satellites that we knew of prior to 2015. And then in the south, this is now the footprint for the Dark Energy Survey, which has really been cleaning up the sky near the Magellanic Clouds, which are here. And now there's other surveys that are coming out. There's MagLights, which is going to be up in this region of the sky here, and other surveys are sort of filling out the space. And this is just showing you pictorially some of the results from the first releases, which showed all these now red circles, which are new dwarf galaxies that we think we're finding are satellites of the Milky Way or of the Magellanic Clouds in the southern hemisphere. So this is just blown up, and we're at a number of around 50 or so right now, and one of the name of the game is to figure out whether or not these things are actually satellites, and that requires spectroscopic follow-up that's being done, for example, by Andrew Pace. And so, this is definitely important work that's coming out right now to figure out how many of these are actually globular clusters or satellites, and what really is a true number of satellites around our Milky Way. Right, so, okay, so the next game changer that's on the horizon is going to be LSST. So LSST is going to image the night sky, and what's plotted here is satellite absolute magnitude relative to the distance that we expect to observe them, or from the sensitivity limits of different surveys. And this is a little bit out of date. This is from Eric Toller's work in 2008. But what you can see is, for a given sensitivity of a survey like SDSS, or here now LSST, right? The red circles are all the different satellites we've observed. So there's a reason why we haven't seen perhaps all the satellites, really faint ones in particular, that might exist around our Milky Way. That's because the sensitivity limits are quite low. But as we go into the era of LSST, we may be able to fill out this space. And so, already some of the new satellites have been detected or kind of filling out at around 200 kpc to 100 kpc from the Milky Way. And we sort of expect that theoretically there should be a lot of satellites around our Milky Way, something on the order of 100 or so, with luminosities greater than about 10 to 3 times the luminosity of the sun, and maybe many more with fainter luminosities. So if you actually take predictions from these theoretical numbers for the LSST, given the LSST sensitivity limits, we should be able to find something around the order of 50 to 20 or so satellites with luminosities on the order of 10 to 3. And then fainter ones, we could find many. We could be finding a lot, something where 50 to 300 or so might show up on their next horizon. And the issue is when we're finding all these satellites, what is that telling us actually? What are we learning about our Milky Way? And how do we actually use those satellites as actual probes that tell us something fundamental about our Milky Way? It's not just about number counting, right? We want to use these galaxies that are sitting out at distances farther enough away from our Milky Way to probe, for example, the total dark matter distribution of our galaxy. So, the interest from my point of view, from my research, is really getting at what is the dark matter distribution around our Milky Way? Right? How much mass is there in dark matter? How is it distributed as a function of radius? And I think the satellite galaxies and other tracers in the halo, which could include streams of stars, it could include globular clusters, are all tracing the potential of the Milky Way. And that potential is dictated by this distribution of this unseen mass. And that's really what we want to get at the end of the day. So we can do this not just by finding these satellites, but also by clocking how fast they're moving and exactly where they are in the sky. And until recently, that just hasn't been possible. So we'll be able to, if you had full 6D phase space information, so if you had the three-dimensional positions and velocities of every single galaxy that's orbiting around our Milky Way, we could, in principle, constrain the total mass of our Milky Way, and also around M31. We could find the distribution of dark matter. What is the shape of the halo of our Milky Way? We could recover the assembly history of our Milky Way. When did these satellites come in? How much material did they bring in with it? Right? Did that actually contribute to the buildup of our galaxy? And are these satellites that are orbiting around our Milky Way, are they actually important for the evolution of the Milky Way's disk itself? Are, for example, interactions between satellites and our Milky Way's disk causing structures that we see today in our Milky Way? Right? So what is actually going on with this interaction with our Milky Way? So this picture here is just sort of showing you an example of what this hierarchical picture that we've been developing over many years might look like. If the Milky Way ate a large number of small things, they may leave debris out at very large distances, forming what we call the stellar halo of our Milky Way. And the issue is, the next generation surveys, LSST, Gaia has just come online, HST, JWST are all going to clock the 6D phase space information of all of this stuff. And the question is, can we relate this then to a model, it's a little bit hard to see, of the dark matter distribution around our Milky Way? How do we make this connection? Okay, so an important concept to just make sure everyone's on the same page is tangential motions or proper motions. So the proper motion is the change, the angular change of an object on the sky over a given period of time. Right? So this is an example of Barnard Star, which is the highest proper motion star that we know about. It's quite close to us and it's moving with fairly high speed, something like 140 kilometers per second. So what's being shown here is just in pictures taken in intervals of 5 years. And what you'll notice is that the stars in the background really aren't moving very much relative to this foreground object, right? So you can basically stack these images, you make sure that the pattern in the back stays constant, and you look at the change of the star that you're interested in over some period of time. So you get an angular change. If you know the distance, then that's a distance over time, hence the speed, right? So this is how we figure out tangential motions of stars. But this is really hard when the object is far away, because the change over some period of time is not going to be as obvious as this, right? So changes we're talking about are milli-arcseconds per year, right? These are tiny, tiny changes. And to do that, you need to A, go to space, and B, you need an instrument with an incredible level of precision. So we have a few of these instruments right now. One is Gaia. So Gaia's second data release should be coming out very soon. And Gaia is going to be a game changer for the structure of our Milky Way. right? What are the internal kinematics of our Milky Way? What does the structure actually look like? Is everything really perfectly flat, or are there ripples? And if there are ripples, are those things moving upwards, downwards in the plane of the sky? And what does that actually tell us about how, for example, the Milky Way may have interacted with other satellite galaxies? Right, so we're going to get an insane amount of data. Data release, I think the second data release is in April, so you're going to have to expect the archive being taken over by people writing papers about Gaia. And you know, this is going to be really important for the Milky Way's disk and the inner halo, something out to around 30 kpc, and maybe for some of the satellite galaxies around 50 kpc or so. But in the outskirts, at farther distances, what we're really, oh, actually I should show this movie first. Okay, so this is how crazy Gaia is going to be. So it's a little bit hard to see this all. I'm not sure if we can make the lights lower just for this one slide. So what you're going to see is these are all the stars that are in the first data release for Gaia. And what they did is they took the first data release and they compared it to the Hipparcos survey, which had it having data already for a while ago. And what you can do then is just like use the change in motion from Hipparcos to Gaia and actually ask then, with that change in motion, over some period of time, that time baseline that you know, can you then get a velocity? And can you then project that velocity forwards in time? So this is our Milky Way's disk. You've got the Milky Way here, and these are all the stars within it. Each data point, it represents an individual star. And then what these folks did is they forward modeled the evolution of each of those stars in the Milky Way's potential forwards in time. And it's really looking at 2 million stars, doing orbit calculations, and what you'll see are stars kind of flying through our field of view. Those are those high proper motion stars relative to us. The whole Milky Way plane is going to shift a little bit. That's accounting for our reflex motion, the fact that we at the sun are actually moving ourselves. And you're going to just see not a static picture of our Milky Way, which is what we're used to seeing, but rather a dynamic one. And that honestly is one of the biggest changes that's happening right now in the local group, is we're thinking about things moving on timescales that we can start to model and understand. Whereas before we've always thought of the Milky Way as a fairly static thing, that we really have no way of measuring changes on any timescale that matters. So, you know, obviously this is being forwarded to, 800,000 years from now, right? But like, because these motions are quite small. But what this really does mean is you'd be able to predict how constellations would change on the sky, right? Because you're actually looking at those motions and clocking that level of precision. So this data is going to be really cool, is I think what I wanted to stress here. Okay, so within the inner 30 kpc or so, this really is going to be Gaia's territory. But when we got out to larger distances, the proper motion errors that we're associating with each of these measurements are going to increase. And you really need something with an incredible level of stability in order to get errors on that are small enough to actually be able to do anything realistic. So the kind of things that we need are characteristic glossy accuracies. Say for a satellite at 70 kpc, we need something with a precision of around the order of 10 kilometers per second. So 10 kilometer per second errors correspond to proper motion accuracies of 30 micro arc seconds per year, right? So remember, arc seconds with fractions of degrees, and add a micro to that. This is how small we're talking about. And we're claiming that basically HST can do this. And this is essentially the speed of human hair growth on the surface of the moon. If you can see that, this is what we're claiming HST can actually do. And in terms of just some more numbers, what this is saying is you can measure changes at 0.006 of a pixel on the ACS or FC instruments over CCDs over a 10-year baseline, right? So this is just really comes down to knowing your PSF, knowing the data very, very well to be able to characterize it, to be able to measure these kinds of changes. So the data is astounding. And then it comes down to theorists to actually do something with these amazing measurements that are coming out. And how do we actually, again, relate this back to what is the dark matter distribution of our Milky Way? All right, so the story of the Magellanic Clouds is a really interesting one, right? These are the most massive galaxies that are orbiting around our Milky Way. And we've known about them as humans forever, right? We call them the Magellanic Clouds in a very Western-centric view, but the Southern Hemisphere, the peoples who have lived there for many, many years, have known about the Magellanic Clouds because you can see them with your naked eye in the Southern Hemisphere, right? So here's the Milky Way. This is a picture in the Patagonia region in Argentina. This is Comet McNaught that was fortuitously passing by when this image was taken. And here's the large and the small Magellanic Clouds. And they really do look like two clouds in the sky. So in the southern African regions, they view them as tracks of celestial animals. I'm just highlighting a few of the different stories that have come out. And there are many, many, many stories, right? Because they're bright on the sky. In the Australian indigenous astronomy, we view them as cranes that were in the sky. And in South America, we view them as two wells, which will be places where you take your horses to get water. And it's just important, I think, to put that perspective in when we think about these kinds of structures. And what's really, I think, unique about local group dynamics, local group astronomy, is that we're talking about structures that are relatable to people all across the globe, right? And are relatable across eons of civilization. Everyone has had a story about the Magellanic Clouds and the Milky Way and various other structures like the Pleiades, for example. And it's important to like really put that in context and just imagine like how much our understanding of what these structures actually are have changed over such a long period of time. But when you're relating and talking about these structures to different people, particularly in the southern hemisphere, they have an importance in there that I think is just important to highlight. So we've known about these structures for a really long time, and all of a sudden in the past like 10 years, our picture of what they've been doing has completely gone out the window. So here's another picture of the Magellanic Clouds. This is a much deeper image. The traditional kind of optical image is put over here, and then if you really did a very deep survey of the Magellanic Clouds, you'd get out structures that go up much larger on the scale here. And we can actually then overplot the direction of motion of the clouds on the sky. So these two galaxies look highly disturbed. They have, the LMC is this bar and this one-arm structure, and then there's all this stuff in the north. The SMC is just a complete train wreck. I'll talk a little bit about that later. But it's, we know exactly what direction these galaxies are moving on the sky now from proper motions with HST. The HST data that's come out, this is work that was led by Nitya Kalivailo, who's currently a professor at University of Virginia, and Roland van der Marel. The data is so exquisite that not only can you track the net motion of the galaxy on the plane of the sky, you can actually get the internal kinematics out from the residuals. This is crazy, like you're actually watching stars rotate within the galaxy. And this is the first time this has ever been done for a galaxy outside of our own Milky Way. So you can get out the internal rotation, so you can actually figure out where the kinematic center is just by watching the motions of stars about some galaxy, or about the LMC center. The SMC is going to have internal kinematics as well coming out soon, and this is being led by one of Nitya's students, Paul Zivik, and what he's finding is the SMC is just like exploding in different directions. It's really crazy, but it's kind of what we expected to happen. So the general picture is that these two galaxies actually had a collision sometime recently, and so if you have two systems colliding, you would expect this small thing to not be happy right now, and it doesn't seem to be internally. So that holds together. Anyway, so this is amazing. The very first paper from the Gaia data release was written by Roland van der Marel. He had like the whole system ready to go because they had done this work where they'd already measured the internal motions with HST, and they wanted to confirm this with the first Gaia data release. So I think this is like paper number 1 of the Gaia data release set back in 2016 that confirmed the measurements from HST. And they were actually able to have more data points where they could measure the internal rotation. So this whole picture does seem to hold together very well, that we now know the motions of the LMC. We've done it now with 2 different instruments. Everything seems to align quite well. And we can actually measure the internal kinematics of galaxies. Just from a broader point of view, the internal kinematics traces also the dark matter within each of these different galaxies. So if we can start doing this for other systems, not just the LMC and SMC, but smaller galaxies, we can really start to get at some fundamental questions of the distribution of dark matter in small things, right? Which is where you can test a lot of different theories about dark matter there. Okay, so what Louis alluded to is the work I'd done as a thesis student was to think about what do these proper motions actually mean then for the past history of the Magellanic Clouds around our Milky Way. And the old picture that has stood for many, many years was that the Magellanic Clouds have always been associated with our Milky Way, that they've been going kind of around and around and around for about a Hubble time. When Nitya's new proper motions came out, they revealed a speed of around 320 kilometers per second, which were higher than what we had thought before. At the same time, there's been a change in the theoretical picture of the galaxy structure. Typically before, around this time, the Milky Way was modeled as an isothermal sphere. And what this means is that the dark matter distribution changes such that the rotation curve stays flat out to whatever radius you want. And in order to do that, you need to have the mass growing as a function of radius, which gives you, in the end, at the distance of the Magellanic Clouds, a very, very large mass. Probably much larger than we realistically think it should have. And when you apply that kind of model, you get solutions where it goes around and around again, because there's like infinite mass in the system, right? You're always going to get something bound. Now, if you take into account that with these new cosmological simulations of galaxy structure, we can actually think about what the distribution of dark matter should be around a galaxy, and we find that it drops off as a function of distance, right? This is logical. The density can't just continue on forever, right, increasing, or the mass can't keep increasing. So when you adopt these new profiles where the density drops off as a function of radius, like an N at W potential, and you take these two things together, you get out a different orbit, which looks more like this blue line. And you get the Magellanic Clouds that are able to go out to much, much further distances over the same period of time. And in fact, within a Hubble time, it's actually quite hard to close this orbit, which would imply that the Magellanic Clouds have only recently come into our neighborhood. They're just past the paracentric approach, which means they're closest approach to our Milky Way at the present time. And this is actually quite a rare configuration. Okay, so this is the kind of the picture moving forward, is that it's possible to close it if the Milky Way is really, really massive, but for most realistic models of the Milky Way that we have right now, it looks like the Magellanic Clouds are coming in for the first time. So I'm going to work with that premise moving forward. So you may disagree with me on some of these points, and remember always, whenever anyone gives you a talk, they're giving you their personal opinion about what they think things are going on. So this is all, my opinion. But I think it explains a lot of things, and in particular, one of the things it explains is what is the mass of the LMC. The LMC itself looks like, we call it a satellite, and because we called it a satellite, because it is orbiting around our Milky Way, we immediately assume that it's small. It's a small galaxy, everything else is small, especially in comparison to our Milky Way. It really doesn't matter dynamically, and it shouldn't be affecting our Milky Way really in any particular way. So there is dynamical data for the LMC. There is a rotation curve. I showed you the data that is showing that it does have internal rotation. And when you look at the rotation curve, it tells you that the dynamical mass of the LMC has to be at least 2 by 10 to 10, at least within 10 kpc or so, right? Now, interestingly, if you take the baryon fraction, so what this means now is if you take the amount of gas and stars that you observe in that galaxy, right, we typically think that the ratio between dark matter and these baryons should be on the order of 3 or 5%, right? So if that's true for the LMC, then the actual total mass of the LMC should be on the order of 10 to the 11. So 10 to the 10 or so within maybe 10 kpc, but the actual mass that that halo for the LMC should have had to have a baryon fraction that makes any sense at all is on the order of 10 to the 11. This is the same kind of argument as abundance matching, which you may have heard about, which tells you about how the distribution, you take a cosmological simulation and you say, all right, I have all of these halos at every given mass bin, and then you look at a survey like SESS and you say I have all these galaxies at every given stellar mass bin, and then you just kind of connect the two. What's the most likely halo for something to reside within? You get the same number, but it's basically the same argument. So, all right, so now I'm saying that the LMC is sitting in a halo on the order of 10 to the 11 solar masses, and you can ask the question, does this really make any sense? The Dark Energy Survey, as I mentioned, found all these new satellites, but it also covers a region of the sky just to the north of the LMC. And they found a fairly surprising thing, which is that there are stars from the LMC that seem to go out to about 18 to 20 kpc away from the LMC center. So, all right, so let me just put this into a little bit of perspective, right? We don't know if this is symmetric, but if it is symmetric, it means that the LMC's disk is 40 kiloparsecs in diameter. 40. It is only 50 kpc away. This thing is huge. Right? In order to explain why there are still stars out at this distance, the LMC can't be 10 to 10 solar masses in total mass. It's not possible. The tidal forces would have stripped this thing apart by now. So these observations are really indicating to us that the LMC is big, the order of 10 to the 11, which would mean that it was, so it's both moving faster than we previously thought, and it's much more massive. 10 to the 11 would put it at about 10% of the Milky Way's total mass. It could be 2 by 10 to the 11, which would put it at like 20% of the total Milky Way's mass, currently sitting at 50 kpc away. Right? That's a huge perturbation to the dark matter potential. So the question that my team is working on right now is, what does this actually mean? So we have this picture now where the LMC has come in fairly recently, it's moving really fast, and it's probably got like 20% of the Milky Way's total mass within a 50 kpc and a radius away from us. Right? What does that actually mean? And should that affect, for example, the motions of streams, stars, collaborative clusters, and satellites? And like I said, we have new surveys coming online that are going to give us the 60 phase space information for all of this. Right? So if we ignore this effect, are we making a big mistake? Oh yeah, there's a whole bunch of other things that I can talk about if you're interested. Like, the fact that it's moving faster and is quite massive has implications for the circumgalactic medium of the Milky Way. For example, there's a bow shock around the LMC. It's moving at Mach 3, which is pretty cool. So if anyone wants to talk about that, we can. Also, the Milky Way's disk should respond to the fact that there's this big thing around. So if you want to talk about the structure of the Milky Way, we can talk about that later too. But what I want to focus on is the halo and thinking about the dark matter distribution over Milky Way.
Actually, I have a quick question. So, so you said like 20% of the mass of the Milky Way is in the LMC. Like, if you look into the simulation, could it have been more equal, like, at the time that they merged together? So in other words, has the Milky Way gained significant amount of mass since they merged, or is this sort of 20%? Is this
right? So
about
is it
where-
all like just like in one blob coming in at it? So the way that we're viewing it is that since it only came in recently,
Yeah.
basically the Milky Way's total halo mass is whatever it was, and then you have
Okay.
this added contribution. It's not going to be in a perfect sphere.
Yeah.
It'll be something distributed, and it will eventually be part of that Milky Way total distribution.
Okay.
It's just that my point is going to be that it's not symmetric. You can't think of it as symmetric. But that's right, it actually ends up being the total mass budget. So should all the satellites then account for that total new change in potential? The problem is, though, that that change happened over a fairly small period of time, right? And it happened asymmetrically.
Yeah.
So are all the satellites already responding to it? Is there some delay time? What is actually going on, and where would you see the signal? Is it, in particular, I'm going to argue that the Milky Way is not in equilibrium. So, yeah. So, okay, if you look at the night sky of the Milky Way, this is with Sloan now. This is the northern hemisphere. We found there's a lot of structure. Each of these kind of, it's a little bit hard to see, but there's like a structure here. And this is just showing you stellar density, now color-coded in terms of line of sight velocities. So they're structures that are coherent in velocity and look like they're quite dense on the sky, so they stand out. So these are structures that we infer are like objects that were once bound that are now being stripped apart. Some of them are from dwarf galaxies, some of them are globular clusters. Particularly the very thin ones we think are globular clusters, which means that their initial dispersion was quite low. And for the larger systems like Sagittarius stream, which like really dominates the night sky, we think it was a fairly large progenitor. So we have all this data about stellar streams, and people are particularly have been focusing on, well, if you have a stellar stream, what this means is that you have an extended distribution of stars, not just one point, like a satellite or a globular cluster. And in particular, you may get multiple wraps around, which will allow you to basically trace back a complete orbit. Now this is really powerful, right? So for example, you have stars moving around the galactic center. When you have a complete orbit, you can actually infer what the mass of the black hole actually is, right? This is how we know the mass of our black hole in the Milky Way. And the idea is similar, a little bit different, but similar for streams, like for example, for Sagittarius. So this is kind of pictorially what the Sagittarius stream may look like. Here's our Milky Way. Sag is a dwarf galaxy that's quite close to the galactic center, so it's around 20 kpc away from us. And its debris is orbiting, in this kind of projection. It looks like it might be roughly this. We have distances to a number of these stars. We have now kinematics, velocities. Once again, new surveys will get full 6C phase space information. And then the question is, if you have these kinds of wraps, can you then infer the total mass of the Milky Way, or at least out to that distance? Right. So this is another simulation which people have used to try and match the data points, which are these black crosses. Right. So you can run simulations. You have an in-body model. You forward model, you allow the Sag to start at some radius, you allow it to orbit along some orbit, and you have to watch it strip apart. And at some point you can change the potential and you'll get different locations for where the stream ends up. And you figure out which potential gives you the best match to the data, right? So this is how you can constrain the potential using stellar streams. Now, the first works on this inferred a dark matter distribution that was really weird. It inferred something that was highly prolate, something that was very long along the z-axis of our Milky Way, and very thin this way. So with that kind of a structure, you would actually not get a stable disk to form. So it really was hard to understand why the data seemed to want you to fit a potential that looked like this. Now, more updated models have also been looking at this, and they're inferring not this, but something much more spherical. Everyone's disagreeing. No one's got a really good answer to this. But what I'm really going to say is that you've got to watch out for the LMC. All right, so here's just going to be diagrammatically where I think the issues are. Here's our Milky Way. I'm going to make this blue circle as being the Milky Way's dark matter distribution. And then there's the LMC sitting at 50 kpc away, right? So in this model, let's say the Milky Way is 10 to the 12 solar masses. And so within about a radius of 50 kpc, that would enclose a total mass on the order of 3 or 4 by 10 to the 11. Right? Now, the LMC is sitting here at 50 kpc, and roughly within 50 kpc, it might have a total mass of around 10 to the 11 solar masses. 10 to the 11 versus 4 by 10 to the 11, this is like a 1 to 4 merger, right, in the inner regions. So what this actually really means is when you have a perturber coming into the inner regions of this kind of mass ratio, where is the dynamical center of that system? It's actually not where you think it was. It's not in the center of the Milky Way. It's actually offset by something like 15 kiloparsecs. This means that the Milky Way's galactic center is going to move relative to the fact that as the LMC approaches, right? This is a two-body problem when the masses are quite similar. The dynamical center is not at the center of the most massive thing. It's changing, and it's causing both of these galaxies to move. Now that perturbation is going to cause, so the center is going to move at a speed of like 40 to 80 kilometers per second, and it'll move by about like 10 to the 20 kiloparsecs. So here's another example of what's going on. This is a movie showing you the dark matter distribution of the Milky Way, and now the LMC falling in. And just focus on the inner regions of the Milky Way, and you'll see that it moves, right? It moves downwards towards the LMC. Now, this kind of perturbation will affect not necessarily the dynamics in the very inner region of the Milky Way, but say you had something out here, right, like a string that goes out to 100 kiloparsec, like SAG, right? Will it have the same sort of torques from the LMC, and will it move by the same amount? Probably not, because it's further away. So you can actually induce perturbations in the orbital planes of satellites because of this, right? And this is happening over the past 50 million years or so. This timeline is quite small. I don't know what just happened there. Okay, PowerPoint. So here we go. Hopefully. Everyone keeps telling me to switch over to Keynote, and I really shouldn't. So this is work that's being led by my student Nico Garavito Camargo, and what we're basically finding is, the distribution of the Milky Way is going to change in both time and radius. And if you don't account for this effect, you're going to get different, basically incorrect answers to what you're kind of tracing back and how you're modeling your orbits for your streams. So this is another example. So this is being plotted here is dark matter density with contours showing you isodensity contours, or contours of constant density. This is before the LMC comes in. I'm just going to assume that everything is perfectly spherical. Right, so you have concentric circles indicating different density levels. Then the LMC comes in, this is about 50 million years ago, and then you can see that the inner regions, these density contours are no longer spherical, right? But the outskirts may be less so perturbed, and some of the inner regions, like the very inner regions of the Milky Way, are probably fine. Then about today, it's over here, and again, you have a completely different axis of symmetry, and that change happened over a billion years. Now that 1 gig-year timeline is important because that's basically the dynamical time of all things moving within the orbit, within the Milky Way's halo. So this new potential changes in time, and how you actually model orbits needs to account for this effect. That's basically the argument we're making. Right, and so we tend to think about the shape of the dark matter halo. We describe it as being spherical, oblate, or prolate, right? Some sort of preferred axis of symmetry, or even triaxial, which still implies some sort of an ellipsoid structure. This thing is neither one of those. It's none of those things, right? You can't properly explain it with any of these traditional models. It doesn't work. Okay, so this is just an example of what I was saying, what might happen to orbits of satellites and streams. So which way does this go? So the red one is saying that we don't allow the Milky Way to move, and we include the LMC's kind of orbit. And what we get is this red orbit for SAG. So it starts here, and maybe it makes over a billion-year timeline. It goes out to an apocenter of 20 kpc, comes back down, and maybe it's someplace around here in continuous orbit, right? So it's going backwards in time. Now, if you start off in the same point, but now you allow the Milky Way to respond to the fact that the LMC is there, the orbit you get out is now this green one that goes out here, and you can see that these two orbits are tilted with respect to one another. There's a different precession that's being inferred. One way you can tell if the potential is triaxial is that you compare orbits, and the orbits precess over time. And what we're saying here is that this precession is occurring, but it's not because it's because of this time evolving effect that the LMC is inducing. Okay, so these are the kind of issues that can happen. So that's one problem, right? How are we actually going to infer the mass of the Milky Way will depend on how we model streams, and we're saying that the halo potential is changing as a function of both time and radius. But what's actually another really cool thing you can think about is there a possibility of actually tracking the passage of the LMC through the halo of the Milky Way? So this is an ATOC projection. The Milky Way would be here. The LMC today is sitting over here. And what you can do is kind of track the orbit of the LMC backwards in time and out to the point where it came into the Milky Way for the first time, right, about 250 kpc away. The color coding is distance. And you can also track it forwards, where it may be in the future, right, going up to the north. So basically the northern hemisphere hasn't really been affected by the LMC particularly. It's mainly in the south. And what we can ask is, are there differences in the way the halo might respond in the north versus the south? And you can make the assumption that stars are kind of in equilibrium with the dark matter. Now you may be familiar with the concept of dynamical friction. So dynamical friction is the reason galaxies merge. And it's basically the assumption here is that the galaxies are moving within each other's dark matter halos. In other words, they're moving through a medium. And a medium responds to the fact that a galaxy moves through it. It causes a gravitational focusing of material around it into a wake structure that trails it. And this wake then pulls back on the satellite or the object that's moving through the dark matter halo, slowing it down, right? So there's a friction term that's introduced. What I like about this, what we're going to show you here is the Milky Way dark matter distribution initially, and then the star is going to represent the path of the LMC through the dark matter halo. Right now, initially everything is assumed to be basically a constant density. And then as the LMC moves through it, this is starting at really large distances away, something like 300 kiloparsecs away, and getting in closer and closer, what you're going to start to see is a yellow distribution that it indicates an increase in density, trailing behind the LMC. This is dynamical friction, and this is what it is. You have an increase in density trailing behind the orbit of an object moving through the halo, and as it moves, as it continues along its orbit, that wake that was induced pulls back on that satellite, causing the orbit to decay, and that's what dynamical friction actually is. Now, what's interesting about that is that dynamical friction is actually a prediction from cold dark matter, or dark matter models in general. It's a particle model, right? That there actually is a fluid or a medium through which an object is moving. And you can ask whether or not we can actually see this effect. This is today, there may be areas of underdensity or high density. The structure is non-linear. It's not very easy to predict analytically what it should do. But the question is, should you be able to see it, the signature of this effect, in the stellar halo of our Milky Way? So like I said, we're going to get 60 phase-space information for all the stars in the Milky Way's halo. And I'm saying that the LMC is moving through it. I'm going to assume initially that everything is perfectly isotropic and everything is smooth, which it is not, because of course there are streams and other things in the halo. And then I'm going to compute the anisotropy profile of the Milky Way's halo. So the anisotropy profile just relates dispersions of stars in the line of sight component versus the tangential component, right? It's saying if everything is perfectly isotropic, the tangential component and the radial component should be the same, right? You get some kind of equal motions both sideways and towards us, right? So we're starting with everything basically being roughly 0. As the LMC sort of walks, we're going to walk with the LMC through the orbit through the Milky Way's halo, and you can see where perturbations start to show up. This is distance, and this is the anisotropy profile. So right now in some of these regions here, we're finding a maximal increase in this dispersion profile, this anisotropy profile in the inner regions, and in some other regions there's kind of nothing. So these are the flat regions are corresponding to the furthest locations, and these blue ones are corresponding closer to where the LMC is today. This is where the LMC actually is today at 50 kbc. There's going to be an increase in this anisotropy profile and a decrease at larger distances. And this is now where the LMC is going to be in the future. The fact that the LMC hasn't even gone into these regions of the sky still shows an increase or a change in the anisotropy profile. Yeah. So this is kind of what it looks pictorially. This is, once again, an ATOP projection. The Milky Way would be here. And there's increase in dispersion in the radial component in particular around the LMC, and a decrease in the dispersion in the north, where the LMC hasn't even been yet. So what we're saying is that the halo of the Milky Way is responding to the fact that the LMC is there. It's responding not just locally, but rather globally. Regions of the sky where the LMC hasn't even been at are responding to the fact that the LMC is there. And this is a prediction. While we can't necessarily tell you the exact number of what that dispersion is going to be, because it is model dependent, as you change the mass of the LMC or the anisotropy profile of the Milky Way, what holds is the relative changes. There's a region of a decrease in the anisotropy and an increase in the anisotropy in certain regions of the sky. And that's a prediction that we can make. So this is just showing you, again, the density distribution. This is that wake structure that trails behind the LMC. So some of the questions we're after is, can we see this signature? Can we show that, for example, dark matter needs to be a particle, that there has to be a medium through which the LMC is moving in the dark matter halo, and can't just be some modified gravity, for example? Or also, can we actually show a prediction for what the increase in density in stars might be along the path of the LMC's orbit, which would tell us exactly where the wake is?
So actually, are you going to show, there's been measures of that big a quantity for halo stars, right? Those measurements today don't give you much.
They're all over the map. They're predominantly in the north. So what we're really saying with this picture is, if you want to find out, I should explain. The anisotropy profile is really important for measuring the mass of the Milky Way. If you assume some basic genes modeling, you can say, well, if the system is in equilibrium and there's this level of anisotropy, I can actually determine what the mass profile of the Milky Way should be. But what I'm saying is that the anisotropy profile is not just a constant at each radius. It changes depending on which region of the sky you're looking at. So most of the surveys have looked in the north because they've been SDSS, and that seems to be okay. Like it's probably fine. But if you were going to do this with stars towards the LMC, you're going to be wrong. And that's really what we're arguing. So we're trying to figure out where are the regions of the sky you can do this measurement and be fairly safe, and where are regions that you should probably avoid. But also they all disagree with each other. All right, so what I'm arguing is that a massive LMC on first infall towards our Milky Way can change the orbital barycenter of our system, right? Where's that dynamical center? It'll change the shape of the Milky Way's dark matter halo. It'll change the orbital planes of satellites, and it's going to change the kinematics of the stellar halo. And then these two in particular have a lot of implications for what we're going to assume for the shape of the dark matter halo or the mass of the dark matter halo. All right, so the last thing I wanted to talk about was like, well, what else can we do with 6D phase space information? We have perfect information of the exact positions and velocities of all these satellites. What can we do, and particularly given that there's such a huge increase in our understanding and models of the from the theoretical side about the distribution of satellites, for example, about our Milky Way. We have these huge cosmological simulations now, which are following structure formation, where you have all these different Milky Way type of galaxies and different distributions of their satellites. We have this huge plethora of data, and how do we connect what's going on in cosmology and galaxy formation and evolution to these new amazing data sets that we're getting out? So my graduate student Ekta Patel has been working out a framework to do this. So what she's saying is, let's use a cosmological simulations like this one, right? It's the lustrous cosmological simulation. There's many other examples where you have some sort of central dark matter halo and a bunch of substructure within it. And let's say we're going to use these as priors. We're going to have thousands of these Milky Way analogs in these simulations. And we're going to then select within there, we're going to assume that we have some data set, which are the observed satellite properties, like the 60 phase space information that we're getting. Right now we have about 9 satellites with proper motions. Soon we'll have many more. But let's start with these 9. So we have a prior, which is just these thousands of Milky Way halos and all of their satellites. You have data that's coming out from these surveys. And then we can create likelihoods to compute for each halo of the prior, right, given a product of the normal distributions that are built around this data set, right? So you can assume kind of Gaussian distributions. And then you create likelihood weights, essentially to create a posterior distribution. I don't really want to get into this, but it's basically it's a Bayesian framework, right? So that given my prior, given my data, what is the likelihood of actually having a Milky Way of a given mass? And this is really what we're trying to get at, right? So in a cosmological framework. Now, people have done this for a few different ways. So what we have is a 3-dimensional velocity vector. We have a 3-dimensional position vector. So one thing that you can straight away say is, all right, my data that I'm going to match are the positions and the velocities of each of the satellites that are observed. So I'm going to look into these simulations of Milky Way analogs and ask, how likely is it that I'm going to find a satellite with a given position and velocity, and what is that mass of the host that is most typical right, so what is the mass of the host that typically hosts a satellite with a given position and velocity, right? That's the question. So when Ekta did this, she creates a whole bunch of different posteriors, and you can actually get out this likelihood for a Milky Way, and when you combine all these things together, and this is really what the plot is to look at. This is the velocity of all the different satellites, and this is the mass of the Milky Way that you would infer through this method. So each individual satellite gives you a different answer, right? And what's a little bit worrisome about this plot is, well, you're always going to be biased by the fastest moving satellite. And this is intuitive. The fastest moving thing is going to give you, for example, the strongest, just say if you did a naive estimate, what is the binding energy of that satellite? What's the total mass required to cause that satellite to be bound to the Milky Way, right? You're going to get the highest mass for the fastest moving thing, right? That makes sense. But each individual satellite is giving you a different answer, and you can be biased based on the fastest moving thing or the slowest moving thing. So you can't just use one satellite to tell you about the mass of the Milky Way. You'd have to take out many. And we're luckily in a space where we are going to take many.
So actually, I forgot, do you have any information, do you have any assumption of equilibrium in here, or like, this is just looking at simulations? And
Just simulations, whatever the velocity distributions
so
are.
no like King's theory or anything?
Nope.
Like this? Okay.
Nope, absolutely not. So yeah, you're just taking the distributions are what they are from the simulations and figuring out what's the most likely host for any given satellite. Now, this one is Leo 1, is a satellite out in the outskirts of the Milky Way that's moving very, very fast. And it has, in the literature, people have said that this is the satellite that's going to tell us what the mass of the Milky Way is, because it's very hard to keep that thing bound. And it's true, it'll give you the highest mass. But it could also be an outlier. You don't really know why it's moving so fast, so you can be biased based on one satellite. Now, the bias is actually, yeah, sorry.
So, is there any reason to think that they have to remain bound? They aren't just on some catastrophic
Right.
hyperbolic orbit?
Yeah, so you would need, for example, free body interactions could kick out a satellite to some very high speeds, for example, right? So what the argument has been is, well, if you look in these cosmological simulations, what's the fraction of which are actually moving on these really high speed orbits? And the answer is very, very low. It is like finding unbound particles, objects just doesn't happen. So we take that as like a premise that these things should be bound. But this assumption, this analysis doesn't actually assume that they're bound at all. It just says this is the distribution, and it'll include really high speed, kicked out things on random orbits as well as part of the velocity distribution. You're just taking, these are the velocities.
And this is with a lustrous?
This is the lustrous, but you could do it with any of the
Does it have the
simulations.
mass resolution to really get down to those low mass
So-
things?
Right, so if you're talking about the classical satellites, we're talking about halos on the order of 10 to the 10th or so, and in which case you can say that they're fairly well resolved. However, there's not going to be very many of them for each of these different simulations, so you have to do some bootstrapping stuff to make the statistics work out. But next generation simulations are going to be better, right? So the illustrative simulation is this like 100 megaparsec box, but they have a new version coming out soon, which is going to be a 50 megaparsec box with much higher resolution, in which case you're going to be able to redo this kind of analysis there. Now, the actual issue, though, with this kind of thing, and this is the classic picture. You take the speed and the position, you say naively, what is the mass that's required to keep this thing bound, right? Modulo the fact that you're assuming it's bound. But the problem with this sort of analysis is that, well, you're assuming that the satellite is at a very typical point in its orbit. The LMC is just past pericenter. That's a really weird place to find a satellite. It's where it's moving the fastest, which means it's going to spend the least amount of time there. This analysis is assuming you're picking a typical property, and it's going to return to you the assumed mass for something that's moving typically at a speed of blah, at a position of blah. Now the problem with that is, like, as we can show the LMC's orbit, so today it's here, this is its closest approach, and you can go backwards in time and repeat this type of analysis, saying, now I'm not going to take today's position and velocity as my data, I'm going to take the position and velocity, 20 million years ago, or keep walking past it backwards in time and figure out what the mass is going to be. So if you watch this top panel here, these are different distributions showing you, if I had a high-speed satellite, this is going to be the likelihood for the most likely mass, and then here's for the position of the satellite, this is going to give me my distribution for my mass, and then I can combine these likelihoods and I'll get out an overall expectation for the total mass of the Milky Way, right? So really, what you'll notice is that here's the position, here's the speed of the LMC. It's a very close position, gives you a low mass halo because it's sitting very close into the center. It's more likely to find low mass things like that. And then it's moving very high speeds. Well, what's the most likely mass for an object with, that has a satellite moving at very high speeds? You're going to be biased to a high mass thing. And then you combine these two and you get something in the middle. Okay, but what happens as you change this in time? As you go further backwards in time, these distributions change because now you're changing a different speed and you have a different position. And the most likely mass for any of those kinds of combinations is going to be different. And in particular, as the thing keeps going further and further back in time, you really start to get masses for the Milky Way that are crazy, like 5 by 10, larger than the local group timing mass together. And so what I'm saying is that this type of method is quite biased. You're looking at a satellite at a specific position and speed in its orbit, and that is not necessarily a typical place to find something like that. Yep.
Sorry, so just made me think about it. So this is assuming that if you're looking at the simulations that you're dealing with just satellites. But at what point do you consider it a satellite versus just something that's part of the stream connected to the galaxy? We can ask you that later. So with that, if LMC is in the first pass, for example, then most of this entire previous life is just around the galaxy on infall.
Yeah.
How would this analysis respond to that? Or is that what you're saying?
That's what I'm saying, that this is what it would do, right, as you go backwards in time. So if you had a full stream, you would have information for all the past, what's going to pass, sort of, assuming that it's tracking the center of mass exactly, which it's not, but yeah. But so yeah, that's right, you could actually see this kind of walking out backwards in time, you would get a different mass at every single point on that
Right, so
orbit.
that's actually what this is showing.
Right, exactly. And so what we're actually going to say is don't use the position and the velocity, the instantaneous position and instantaneous velocity, rather use the angular momentum. Because the angular momentum is actually conserved along the orbit. And so that movie showed these two curves bouncing around, but you'll notice at the bottom here, this one stayed exactly the same. And what this is now computing posteriors using not the position and velocity as my data points, but rather the angular momentum, the specific angular momentum of the satellite, which stays pretty much constant. So even though this movie is going to once again show you, as the LMC is going backwards in time, this curve here tracer is just staying pretty much centered at around 10 to the 12. Because it's just using what is the typical host of a satellite with an angular momentum that's the same as the LMC. And that just stays constant along the orbit, so you're always going to get the same answer, right? Which you should. Okay, so if you repeat this exercise now, not using the position and the velocity of every satellite, but rather the specific angular momentum, this is now angular momentum scaled with halo mass. Each different satellite still gives you a different answer, but these now are much more robust measurements because they're not going to be dependent on the specific position and velocity that you're finding the satellites at. And when you combine this analysis, you're going to find that, the total, these are 9 satellites of the Milky Way. You get a total mass for the Milky Way of 0.9 or so by 10 to the 12. Now, this distribution of angular momentum here is being dominated by 2 satellites, essentially. Leo 2, sorry. Leo 1 was that high-speed satellite, but now Leo 2, as the highest angular momentum satellite, is the one that actually is setting the upper bound for your mass of your Milky Way. And then Sagittarius dwarf, that dwarf that I told you created those streams around the Milky Way, is the one that's biasing you low. This is actually a dangerous place to be, because the issue here is that Sag, as a disrupting satellite, has its angular momentum changing as a function of time. And I told you this analysis breaks down once you start changing things with time. And so what we're saying is don't use Sag. Sag is a really bad tracer of the mass of the Milky Way. And it biases you low. If you take out Sag and you recombine all these likelihoods, what you get out is the mass is closer, you can't read it there, but it says 0.96, it's closer to 10 to 12. So you get up to a bit of a higher value, which is closer to where we think it probably should sit at. But Sag will always bias you low, and this is actually similar to what's being found in the literature. People are trying to model the stream of Sag, and they're always getting lower numbers for the mass of the Milky Way than what we might normally expect. So what we're saying is don't use it, because it's angular momentum is changing as a function of time. It's in the process of being disrupted, so it's biased tracer. Okay, so yeah, the really nice thing about this type of analysis is that there's no assumption about the satellite being found, and in the near future, we could probably apply this to M31. So in the last few minutes, I just want to talk a little bit about M31. Here's our Milky Way, there's the Andromeda Galaxy. And we can kind of zoom in on this. This is going to be showing you a movie. The HST promo team, led by Tony Son, had created the first proper motion measurement of M31 in 2012. Surprised, the tangential motion of M31 had never been measured before 2012. You may not have been aware of this. I wasn't. Like you would have thought, it's like the next biggest thing around. We should know what it's moving, how it's moving, right? We didn't. Which means you really couldn't figure out when it's going to hit us. It has a radial velocity that's moving towards us, but we couldn't actually tell. So this is now looking at proper motion. So what you're going to see are stars in M31 that are moving with respect to some background set of galaxies here that don't really move, right? So when you stack these images, you can once again create a proper motion measurement of M31. The issue is that this proper motion is so small. We're talking about 12 microarc per second accuracy. This is why this year is 32,000 in the future in order to actually be able to see it by eye, what's happening, right? So, you're watching, again, relative motions, the change of these stars with respect to some field that doesn't change over some period of time. So, with that measurement, we can actually now revisit the question of when is M31 going to hit us? So M31 is coming directly towards us. We know this because of the Doppler shift. We know that it's coming, it has a blue shift. It's coming straight at us. But is it coming straight at us, or is it coming at some angle? And the answer to that will depend on what the proper motions are telling us. And it turns out that the proper motions say, no, that sideways motion is really small. It's pretty much coming straight at us. And that tells us, we can do the calculations, that in about 3.87 billion years from now, these two galaxies are going to smash into one another. Now, we don't, this doesn't include the LMC, which I think can change this number a bit. There may be some work coming on soon about this. But regardless, it is pretty much going to hit us directly. And when that happens, I think it's just always fun to think, once again, back to our night sky and how important it has been for human civilization. So here's like the picture of the Milky Way, and there's Andromeda today. But in the future, as M31 gets closer and closer to us, it's just going to get bigger and bigger on the sky, right? And it's going to dramatically change, like our bit, as humans, just thinking about the night sky, and as it actually hits for the first time, there'll be these episodes of star formation. This is not a simulation, by the way. This is just like pictorially, done some amazing pictures from observers put into these here. And then in 4 billion years, once again, more star formation. And at 4 billion, they're going to pass through one another and move further away. And eventually, within 5 billion years, they'll have come back together and completely merged. And you can ask the question of what is astronomy going to be in 5 billion years? And the answer is local group. We'll see nothing beyond this, right? So it's like job security forever. So, here you go, right? So it really will be our night sky completely change, and this is these kinds of simulations of dry mergers, which just means they have very low gas fraction, is really where our theory of how you change spiral galaxies into ellipticals really are. And with the best information that we have, this is all kind of fun, but we've actually done these simulations using M31 as a rotating disk with the best information we have about the inclination of the disk, its total mass, and it ends up being an elliptical. So this is part of where that theory comes from. It's not the only story, but certainly there is this idea that if you have very low gas fractions and you put two spiral galaxies in together, you do get an elliptical galaxy in the end. Okay, so I think I'm going to stop there. So I'm just going to pass through this. Oh, I'll just quickly mention that this is M31. These are all the satellites on M31. There's going to be data for 60 phase space information for a bunch of these satellites coming out soon. So everything I told you about what we can do around the Milky Way, we're going to start to be able to do around M31. And with James Webb, this is going to be really cool, right? So people think there's this plane of satellites moving in some coherent direction, and we can now check whether or not they're moving in and out of that plane. That's going to be interesting. So conclusions are, we need high accuracy proper motions of the local group at distances at like 50 kpc or larger, and that really is still the regime of HST and JWST. Local group dynamics are not well understood. The biggest changes are owing to the most massive satellites. And the LMC is likely on first infall, which is going to change the halo shape and the stellar kinematics of the halo. So, great, thank you.
Do we know how long ago and how far away the LMC formed?
Yeah, good question. So we think that it formed within the same overdensity that the Milky Way and M31 formed. And it's just that given the kinematics at early times, it sort of moves out on a very long period orbit and then comes back in. So for the most part of its evolution, it's been evolving in isolation, and it's only now entering back into our environment. But if you do this calculation kind of going backwards in time, you can get it to all coalesce together, or start together. Everyone's depressed because it's like, oh, local group astronomy can take over. Like all there is, and now I told you the Milky Way is changing in time and radius, and there's no hope for anything. No, but it's okay. Like we really are going to create more models for the Milky Way's dark matter distribution now and provide it to the community, so that you can actually start to orbit, integrate orbits in a time evolving potential. So the idea is that everyone will be able to work together on this.
No question. The SMC, like when you were doing your angular momentum and stuff, the SMC and that wasn't a player in this game at all, right?
Yeah,
so,
we took it out, and part of the issue is that like you could do the analysis if you assumed SMC is by its own thing, but it's not.
Yeah.
And so I think it's also a bias tracer. Just like I just don't think it's worth it to do this
So
kind of
what do you,
analysis.
so you think the LMC is big? Like, do you think the SMC is like big as well?
So-
Relative to what people thought it was?
I think it's bigger than what people have thought it was. Typically, people assume that its dark matter halo is like a few by 10 to 9. It's probably closer to a few by 10 to 10,
Okay.
right? So you have to start off that way.
Okay.
But over time, even starting with that, it will get shredded.
Yeah.
But it can't be much bigger than a few by 10 to 10. Now remember, their interaction starts like 5-6 billion years ago, right? So at that point, it may not be as massive as you would infer it to be today, given its variance, right? But if it were much, much more massive, the two should have merged by now.
Yeah.
Right, so there's a limit on what that mass ratio can be, and it's about 1 to 10. So one of the things I did as a graduate student was created a whole bunch of different simulations of the LMC and SMC interacting with each other. These two satellite galaxies that we see today as two distinct things on the sky. We know they have a separation that's quite large today, like 20 kiloparsecs, which means that they can't have gotten that close together in the past. I think they collided, but that's a fairly recent thing. And so if you change the mass ratio between the two systems, this dynamical friction that I mentioned will cause the orbits of these two systems to decay much faster, and you'll actually get the system to coalesce. The only way to avoid it is to put them on a really eccentric orbit and have a mass ratio of around 1 to 10. And if you make it anywhere near circular, they'll merge no matter what you do, just because the LMC's dark matter halo is so big. But if you have an eccentric thing that's orbiting around the Milky Way, that gets split apart really, really fast. So the only way to explain why they're even close together today is if they came in recently. That's my other argument for why they're on first infall.
Okay. I have one more question unless somebody else does. So you're saying the center of the Milky Way galaxy moved at some point in the not too distant past. Is there like any features in the disk that would
Right, so
be instigated based upon this? Or
for the motion itself, probably not. And the reason is just because the whole center sort of moves together.
Okay.
So, but the outer halo and the inner halo will move in different levels.
Okay.
So.
So like the outer stellar halo, okay.
Yeah,
And
exactly.
the kinematics and the distributions of the outer stellar halos are different.
Well, I mean, there's presumably breaks in the density
Yeah.
profile, and there can be changes in the kinematics, so.
Can the story be
Yes.
brought in or no, or?
Well, I mean, I think that's part of it, right? Like, what's going on in the outskirts, I think, is related to this. So how you may have, and those images I showed of the stellar velocity field are going to capture that, right? They'll capture both the fact that the Milky Way is moving and that the LMC is inducing torques. It's gonna be hard to disentangle it all, but you get the net effect of both things. So what we found is within 30 kpcs, it stays pretty much isotropic no matter what.
Okay.
But as soon as you get out to 40, 50, or whatever, everything kind of goes bad.
Okay. So like a lot of these questions are going to be answered in the end of April when people flood the archive of Gaia papers in terms of just like what's the proper motions of, they might measure that, the anisotropy is stellar halo better, or people are going to measure orbits of, larger fraction satellites, correct? So-
Right.
Okay, so.
Yeah, at least within about 40 kpc. The problem is, will they actually get out further? Maybe RLRA is the way to go, probably BHB stars, things like that. So there's a few tracers you can get out further with. I'm not entirely sure how much better it's going to be though. Within 40, it'll be great, but I'm saying that within 40, it doesn't really, honestly, doesn't really do much. This is why I'm like not as excited as this guy as I would have been otherwise when I realized that. But yeah.
And on that, everybody's very excited about Gaia. All right, okay, so let's thank Gurtina.